Hi, this is TheoryStation, and I'm John Duggan. This program is Rational Choice Modeling. The series we're in is called Basic Formal Theory Toolkit, and this is installment 5 in the series. So in the previous installment, we talked about this one-dimensional policy choice model, and then I extended that by having a set of feasible policies, and we looked at the optimal choice from this feasible set, and then I promised that we would look at a model where this feasible set sort of came out of a more intricate model of politics. Again, this is not going to be too advanced, but so now let's look at the one-dimensional policy model with a veto player. All right, so the setup is the same initially. Here we have a policy space. We have a policy space. We have an ideal point, and then we have a utility function for this politician. Again, there's different, specific functional forms we could use, but we can just write down the quadratic one. Now, instead of writing down a feasible set, I'm going to think about a model where there's another decision maker. It could be another politician, or it could be a voter. But basically, I want to think about our first politician making some policy proposal, but in order for that to actually become policy, it has to be approved by a second decision maker. Okay? In this application, I'm just going to call that person a voter. I am going to give that voter Euclidean preferences. That means they have an ideal point. Right, so we're going to have two ideal points in this model. All right, now, and this voter is also going to have Euclidean preferences. I'll give them a quadratic utility function, but now, of course, when we're assigning utility for the voter, we're going to look at the distance from the voter's ideal point, v. Now, to distinguish these two utility functions, if I just use u for both, that's ambiguous. So I'm going to identify the utility function by subscripting it with a p or a v. And that way we'll know if we're talking about the politician's utility or the voter's utility. All right. Last element that we need here. Let me get to it this way. So we're going to imagine the politician making a policy proposal, and then the voter has to decide whether to approve that policy. But that means that the voter has to compare the proposal to something. That's something I'm going to call the status quo. Okay, so well, this is even though it's a fairly simple model, it's really another level of complexity beyond the plain vanilla policy choice model. We now have what is called strategic interaction. We have two decision makers, and so we should, think for a second about how this is going to work. What I'm going to do, well, we're going to apply the optimality principle to both decision makers. Okay. So for the first decision maker, the politician, they have to choose this policy proposal in an optimal way. That's the edict of this optimality principle. What does that mean, though? Well, for the politician to choose optimally, they have to have some expectations about what this voter is going to do. If the voter will approve the politician's ideal point, well, that's clearly optimal. Otherwise, though, the politician has to, figure out what is the best thing I can get approved. This process requires the politician to anticipate the response of the voter to different policy proposals. Now, in this basic kind of model, we're going to assume that the politician knows the voter's ideal point, the politician knows the preferences of the voter, so they basically know the voter likes things closer to V. All right. But we're also going to impose this optimality principle on the voter. For the voter, things are somewhat simple, though, right? Because they get a policy proposal from the politician. They can either approve that or they can stick with the status quo. So by the optimality principle, if the policy proposal is closer to their ideal point, they will approve it. If it's further than the status quo, then they're going to reject it and stick with the status quo. So the only point of ambiguity here is what if the policy proposal is exactly equidistant from the voter's ideal point as the status quo? Okay, in that case, the policy proposal and the status quo, they're the same distance from the voter's ideal point. So the voter does not have a preference for one over the other. We say they're indifferent. In that case, the optimality principle doesn't actually have any restrictions on the voter. They can approve or reject. What we're going to do for this simple model, for this first-time analysis, is we're going to assume that the voter will accept if indifferent. Okay, there are game theoretic reasons why that's kind of without loss of generality, but we're just going to stick with that. Okay, so where are we then? So let's think about the voter's optimal choice. Okay, let me put the policy space on this real line. And, well, where do I put these guys? Let me just see how I want to do this. All right. We'll put the status quo over here and the voter here. Now imagine that that the policy proposal that the voter is considering is here. That's closer to V than the status quo, so they're going to accept that policy proposal. Over here too, a policy proposal at that blue dot is closer to the voter's ideal point. They strictly prefer to the status quo. Let's look at a third option where the policy proposal is way over to the right. That's further from the voter's ideal point than the status quo, so they prefer the status quo. They're going to reject that policy. Now, you can probably see this, but if I just look at this difference between the status quo and the voter, if we just take that distance and sort of shift it to the right of V, we get an interval, and anything in this blue interval is closer to the voter's ideal point than the status quo, except the endpoint where it's the same distance. Okay, so by our optimality assumption for the voter will accept any proposal in this interval. We can call that the acceptance interval, and they're going to reject anything outside because it's further than the status quo is from their ideal point. Okay. We can actually solve for this right-hand endpoint because whatever that endpoint is, let me call it R for right hand, we know that R minus V is the same as V minus Q, and so R is just 2V minus Q. So a little algebra, but that gives us the right-hand endpoint, which is 2V minus Q. We have now figured out how the voter would respond to any possible proposal, again, assuming that they accept when indifferent. Having done that, we can now return to the politician's problem, and we can apply the optimality principle to the politician. So, so let's suppose the politician is over here. Here's B. So now there is a, we have the whole policy space from -1 to 1. Those are conceivable policy choices, but there's only a small interval here, a smaller interval, that actually will get approved. And so in effect, this acceptance interval is like a feasible set. It's like the feasible set we had in the previous installment. And then, since there's an interval of actually available policies to the politician, we know how the politician chooses. This guy, since his ideal point is outside that interval, will just choose the closest thing in the interval to it. Okay, so so they'll just choose 2V minus Q. Of course, if you're lucky and you're a politician and your ideal point's closer than the status quo to the voter, then you'll just propose that, and that'll be accepted. So so that's how the model works with the veto player. Once we have that, we can do the same comparative static if we vary the politician's ideal point, but we already did that. We already know what that looks like for a fixed feasible set. There's no point in doing that again. However, here we actually have a new element of the model, the status quo. And we can think about doing comparative statics on that. That's a parameter of the model. And as we vary that, that's going to affect the optimal policy of the politician. In fact, just the way I've drawn it here, you can see if I were to increase Q so that Q shifts to the right, then that acceptance interval is going to become smaller. It means the voter is going to be more selective about what policies they're going to accept. And that means that the politician is going to have to, in fact, I'll just indicate this with red. So if the status quo moves to the right, then the acceptance interval will become smaller. Maybe it's like this. And the politician will, again, choose the closest thing they can that will be approved. And that, as you can see, has moved to the left. All right, we can graph this, sort of how we did before. So I'm going to represent the policy space on both axes here, but the horizontal axis is going to mostly do the work of telling us where the status quo is, and the vertical axis is going to tell us policy choices. Okay, so for this, I'm going to, when we do this kind of thing, we are changing one element of the model at a time. Here I'm moving the status quo, so I'm going to keep P fixed, and I'm going to put P right here. And also V is also going to be fixed, so I'll put V here. Okay, so let's think about how the optimal policy choice changes now with respect to the status quo. Let's just take the easy case first. Suppose the status quo is somewhere between the voter and the politician. Suppose it's here. The voter will accept anything that's closer to their ideal point than the status quo. And, so we have an acceptance interval, like this blue region here. And clearly the politician is just going to choose the right-hand endpoint, which is the status quo. That's true for any status quo in this interval. So what that tells us is that over that range, in fact, let me just draw in the 45-degree line here. Over that range, the politician just proposes the status quo. So the graph of the optimal policy choice just falls on the 45-degree line. Things get a little more interesting when the status quo is not between V and P. So what about status quos to the left of the voter's ideal point? Well, suppose the status quo is here. The voter will approve anything that's closer to their ideal point than the status quo. So that gives us an acceptance interval like this little blue area here. And the politician will choose the right-hand endpoint of that. And we know the right-hand endpoint. We know what the formula for that is. It's 2V minus Q. So, so for any status quo to the left of the voter's ideal point, the optimal policy choice is 2V minus Q, which looks something like this. Okay. Finally, let's just get rid of some of this stuff here. And finally, what if the status quo is to the right of the politician's ideal point? Well, now the politician's ideal point is closer to the voter than the status quo. So the politician can just choose their ideal point. And so their optimal policy for any status quo to the right of P is just going to be, they're just going to propose their ideal point, and that'll pass. So this blue kind of piecewise linear function, this is the optimal policy choice as a function of the status quo. All right, so that's a different comparative static we can do, and it's interesting that you can see that because to the left of the voter that optimal policy choice is decreasing. That means as the status quo moves toward both players or both decision makers, the politician's optimal policy moves to the left. The voter's leverage, so to speak, is increasing, but then once the status quo crosses the voter's ideal point, the voter loses all leverage. Not all, but starts losing leverage as the status quo keeps moving. So, so there's a more complex model of politics. It shows how this feasible set could come from some underlying model with two decision makers. The term that's used sometimes is that we've endogenized the feasible set because now it's coming out of the model rather than something that we're just assuming. All right, anyway, so that's enough for this installment. In the next installment, I want to look at I'm going to stick with the one-dimensional policy model because it is such an interesting thing to play around with. What we did right now is we added a voter. And what I want to do in the next installment is add multiple voters and see how that changes things. And we're going to see that, it can in a general model, but I'm going to show that with some pretty natural structure, in fact, it doesn't change the analysis at all. So that's coming up in the next one.